Hey folks, it's Miss Manili. I'm sorry I can't be in class today, so I wanted to give you a short, down and dirty lesson on how to find the sum of a sequence. So last class we talked about two different types of sequences, the arithmetic and the geometric. In one of those sequences, you are constantly adding or subtracting the same number to each term. And in the other, you are constantly multiplying or dividing by the same term to each member of the sequence. So let's get started with the warm-up. You should have completed it at this point. You are given a sequence of numbers, 9, 27, 81, and 243. And I think if you look at how quickly those numbers are getting large, it's probably pretty obvious that we're not adding or subtracting the same thing to each term, that we're actually multiplying. So you can probably sense that we are dealing with a geometric sequence in this case. And the way that you can confirm that is to try to figure out what the common ratio is. And the common ratio, again, is just the thing that we're multiplying by. And sometimes you can look and see and you know exactly what we're multiplying by if you have, if you're really good with your times tables, but sometimes the numbers get kind of big, like, from 81 to 243, that's a big difference, and I can't really do that math in my head. So I'm going to talk to you about how to actually calculate the common ratio or the common difference if your numbers are getting a little bit big. What you want to do is you want to start with the second number in the sequence, and so to find the common ratio, I would take the second number, that 27, and I would divide it by 9. And that should be the same as if I were to take 81 and divide by 27. And that should be the same as if I were to take 243 and divide by 81. Now, you obviously don't need to do this 3 different times unless you want to verify that this is, in fact, a geometric sequence. So if I take 27 divided by 9, I get 3. So let's make sure that when I take 81 and I divide it by 27, I still get 3. And if I take 243 and I divide that by 81, I still get 3. So that's my common ratio. And that's going to be important. Well, that's actually the answer to the next problem, right? The common ratio would be 3. The other way that you can check, like if you kind of sense, like I think it's probably 3 because I know 9 times 3 is 27, then you can sort of go through the process. So if I take 9 times 3, I get the 27. And then if I take times 3 again, that gives me 81. Now, because the last command is just taking the previous answer times 3, I don't actually have to type it in again. I can just hit enter, and I get 243. So that would be another way to check that I've got a geometric sequence and the common ratio is 3. Now it asks me to write an explicit formula to represent the sequence. And if you remember from your formulas from last class, that's going to be a sub n. That means any term in my sequence, a sub n is the nth term, is going to be equivalent to taking my first term times the common ratio. And since I'm constantly multiplying the same thing over and over again, I'm going to use exponents, and that's going to be n minus 1. And I need to replace the a sub 1 and the r. And again, a sub 1 corresponds to the very first term in my sequence, which is 9. So this formula, a sub n, becomes 9 times, we already found the common ratio to be 3, and then n minus 1 is the exponent. And I'm going to keep the n there. The n corresponds to like when you have a regular equation and you use x and y, the n would correspond to our x value or variable, and the a sub n would correspond to y. And then the last thing it asks is, what is the 10th term in the sequence? Well, the 10th term would correspond to a sub 10. So I'm just now letting n equal 10. And so when I plug this in, I'm going to have 9 times 3 to the 10 minus 1. And I can plug the entire thing into my calculator exactly the way I've written it. So 9 and then in parentheses 3. And then I want to raise that to the power of 10 minus 1. Now, if you have one of the newer calculators, you'll see that your cursor has been moved into that exponent position. So anything you write there is going to stay in the exponent. If you have one of the older calculators, you might have to use your caret button and you'll actually see it on the screen. And it's going to be important that you put parentheses around your exponent. Like I said, if you have one of the newer calculators, you don't necessarily need the parentheses, but if you have an older calculator, you do need those grouping symbols because your calculator needs to know that you're raising 3 to the 10 minus 1 power, not raising 3 to the 10th power, getting an answer, and then subtracting 1. And you can see it's a really, really, really big number. Looks like 177,147. All right, let's take a look at the next one. In the next one, it's -2.5, -2, -1.5, and then -1. And if I look at those numbers, they're not changing dramatically, so I'm guessing probably this is going to be the arithmetic sequence just because it doesn't look like the numbers are growing very large or very small very quickly. So if I want to double check, the best thing to do would be to go ahead and find that common difference. And just like I did with the ratio, I'm going to take the second number, -2, and I'm going to subtract the first number, which also happens to be negative. And so that number, let's do that, and keep your negatives in there. So it's -2 minus, and then in parentheses, I'm going to have my -2.5. And the minus and the negative are ultimately going to cancel each other out. But it looks as though my common difference is 0.5. And I can check that if I start my sequence with -2.5, and if I add 0.5, that gives me -2. And if I add 0.5 again, that gives me -1.5. And if I press enter again, it'll add another 0.5, and I can see that I'm constantly adding 0.5, so this is in fact an arithmetic sequence, and with a common difference of 0.5. The explicit formula then for a arithmetic sequence, again, we start with a sub n because that represents any term in your sequence. I'm going to have my first term, and in this case, my first term is -2.5. And then I'm going to have plus my common difference, which is 0.5. And this time, since I'm constantly adding, that's going to correspond to multiplying by n-1. And so that's the explicit formula for an arithmetic sequence. If I want to find the 30th term, then I'm just going to let 30 correspond to my n value. So I'm going to find a sub 30. And that's going to be -2.5 plus 0.5 times 30 minus 1. And again, I can type that right into my calculator exactly the way it appears. -2.5 plus 0.5 times 30 minus 1. And I'm going to keep those parentheses in there. And I get 12. And so that's going to be the 30th term. Cool. Today, we're going to take this one step further. And let's put it in context. Well, actually, before we do that, let's recap. Okay, so let me make this a little bit bigger so you can see it. Characteristics of an arithmetic sequence. Okay, so the very first term in an arithmetic sequence we always call a sub 1. That's the first term. And that's going to be true for both the arithmetic and the geometric. And then, and that's going to be where it starts. And then it says, how do we find what's next? So with arithmetic, we have a common difference. And we call that D. And that's the number that we're either adding or subtracting to every term. With geometric, we have what is called a common ratio. And that's going to be R. And with the common ratio, it's actually what we're always multiplying. If you're constantly let's say you're dividing by 10, that's going to be the same thing as multiplying by 1/10. If we're dividing by 2, that's the same thing as multiplying by 1/2. So if your pattern involves division, so if we're dividing by 5, for example, that's going to correspond to multiplying by 1/5. And you can certainly change any of those fractions to a decimal if you want. But when this is your pattern, this is your actual common ratio. You want to turn it into multiplication. We also just want to reiterate what the formulas are, the explicit formulas. If it's arithmetic, any nth term is going to be our first term plus the common difference times n-1. And for geometric, again, we're going to call it the nth term is equal to a1 times our common ratio. And I'm actually going to put that in parentheses. And I'm going to raise that to the n-1 power. And I'll put that in parentheses as well, just to kind of, just to reinforce that proper notation. Okay, so now let's take a look at a word problem, a situation where you might actually apply some of the stuff, because it may sound silly, like why do we have all these patterns of numbers? What's the point? Well, if there's ever a zombie apocalypse, you might want to know. And in this first example in your classwork, actually, if the teacher could go ahead and pass that out to everybody. Um, it mentions that 25 people on a metro commuter bus are exposed to a contagious airborne virus that causes headaches and stomach cramps. An hour later, the passengers on the bus have spread the virus to 75 other people. The following hour, 225 more people have been exposed. Suppose the virus continues to spread at this rate for the next 24 hours. You're asked to write an explicit formula to model the number of additional people exposed to the virus each hour. So let's think about this for a second. We had 25 people the first hour. We had 75 people the second hour. And then we had 225 people the third hour. And that's just the new cases of people that have been exposed. That's not the total number that have been exposed, which is another quantity that we're going to want to look at today. So if that's my sequence, and I know it's going to continue, that's what those dots represent. It just means that it's going to keep continuing to spread. I want to write an explicit formula. So let's first make sure that we understand which type of sequence we're dealing with. Are we adding a constant, or are we multiplying by the same number over and over again? And I think you can see, because the numbers get large pretty quickly, that we're dealing with multiplication. So this is a geometric sequence. And again, just like what we did on the last slide, if I want to write an explicit formula, it's going to be a sub n is equal to a sub 1 times r to the n minus 1. And so what we need to figure out are the values of a sub 1 and r. Well, a sub 1 is just going to be the first term. It's the initial amount of passengers on the bus that had these symptoms. So that's going to be my first term. So a sub 1 is going to be 25. And then I need to figure out my common ratio. And again, I can do that. If you can't see it in your head, you're just going to take the second term and divide it by the first. And we're going to get 3. And to check to make sure that it works, you can use your calculator. So if I take 25 times 3, I get 75. And if I take times 3 again, I can see that I get the 225. So I know that that is the pattern of this virus spreading. And so now I have the value for my initial term and the common ratio. So now let me go ahead and finish up my formula, right? 25 times 3 to the n minus 1. And then it asks, if the virus continues to spread at this rate, estimate the number of people affected in the 12th hour. So if I'm looking for the 12th hour, I'm looking for the 12th term in the sequence. And so if I do that, I'm just going to take my 25 times 3, but I'm replacing the n this time with the 12. And again, we can do this on the calculator. Let me actually make this a little bit smaller. And then I can have the calculator up at the same time. Okay, and so I want to take 25 times 3, and I want to raise that to the 12 minus 1 power. Oops. There we go. And woohoo! So that looks like 4,428,675 people in 12 hours have been infected by this virus. That's crazy. And so the next question says, suppose that we want to determine the total number of people exposed to the virus in 12 hours. To determine the total number of people infected, we need to determine the sum of the first 12 terms in the sequence. So I could totally do this by hand, right? I mean, I could say, all right, my first term, like if I list all my hours, right, for 1, 2, 3, 4, 5, 6, I mean, I could keep listing them. And then I had 25 people in the first hour. There were 75 people in the second hour. There were 225 people in the third hour. And then I could certainly list them, but obviously you can see how big these numbers are getting. If I list them all, then technically I could certainly add them all up, but that's going to take an awful long time to do. There's actually a shortcut. We actually have a formula that will enable us to find the sum of a geometric sequence. And this would be a finite sequence. So that means that I'm looking for the first 10 terms, the first 12 terms, or the first 19 terms, or the first 900 terms, but it's a specific number of terms that I'm looking at. And this is the formula. And so you'll notice that I'm using the capital letter S to represent the sum. So that's a new terminology. We learned about the A and the subscripts. So when you see the S sub n, that's referring to the sum of the first n terms. And then we get to decide, or the problem will tell us what n is. And in the formula, the a sub 1 that you see, that again, that just corresponds to the first term in the sequence. And then the r, that corresponds to our common ratio. And you'll see that that appears twice in the formula. And n is just the number of terms that we're adding together. Okay, so if we wanted to know the total number of people exposed to the virus in 12 hours, well, let's go ahead and write down all the pieces, right? We said a sub 1, if we look on that previous page, we said a sub 1 is 25. And the value of r, we said, was 3. It's tripling every hour. And we want to figure out the total in 12 hours. And so those are the 3 numbers I need for this formula. So the sum of the first 12 hours, that's what that notation means, is going to equal a sub 1, which we said is 25. Let me use a different color here. A sub 1 is 25. And then in parentheses, I'm doing 1 minus my ratio, which is 3. And that's raised to the n power, which is 12. And then I close my parentheses. So notice that 3 is being raised to the 12, and then I close my parentheses. And then I want to divide by 1 minus r. And again, this needs to be in parentheses. 1 minus r would be 1 minus 3. Okay? And so what I'm going to do now is I'm just going to plug that into my calculator exactly the way it appears. So it's 25, and then in parentheses, I have 1 minus 3 to the 12th power. Now be really careful here, because notice that your cursor is in the exponent. In order for me to close the parentheses of my numerator, I have to move my cursor back down. And this really only applies to some of the newer calculators. The older ones don't do this. So I'm just going to use my right arrow, and I'm going to push it back down to the regular line so that I can close my parentheses. And then I want to divide by, in parentheses, 1 minus 3. And it is really important that you have the parentheses there, otherwise the calculator is just going to divide by 1, get an answer, and then subtract 3. And so when you press enter, you can see that in 12 hours, if you were to add up all those numbers, we have over 6,643,000 people total affected by the virus. That's crazy. Now, if this was a zombie virus, we'd be in trouble. All right. Let's take a look at some other situations. And in these situations, I'm giving you the explicit formula, and you're asked to find the sum of the first however many terms. To find the sum, it's the same formula as before, but you have to consider what the first term and the common ratio are from the equation now. So notice that number 1 is written in function notation. It says that f of x is equal to 2 times the quantity 0.75 raised to the x minus 1. So the 2 in front, if you remember your explicit formula, right? Our explicit formula, we use the letter n, or I'm sorry, the letter a sub n, and that's a sub 1 times r to the n minus 1. And so if I look at this formula, I can see that the 2 in front is going to correspond to a sub 1. And the number that's being raised to the power is going to correspond to my r value. And notice that I'm using x's here instead of n's. I know it can be confusing sometimes, but it's actually the same thing. Look at the format of the equation. It's essentially the same as the explicit notation that we used with a's and n's. So if I want to find the sum of the first 10 terms, let's go back to our formula for a second. I'm going to take my first term times 1 minus r to the n, and that's going to go on top, so let me just write the formula. My first term times 1 minus r to the n, and all of that is going to go over 1 minus r. And if I know what r and a sub 1 are, then I can just substitute those values into the equation. And like I said, from the equation up here, from my explicit equation, I know that a sub 1 is 2, and my common ratio, r, is 0.75. And so now I'm just going to plug those numbers into my formula for the sum. We said a sub 1 is 2, and I'm going to do 1 minus 0.75, and I'm going to raise that to the n power, and in this case, 10 is n. And I'm going to divide all that by 1 minus r, or 1 minus 0.75. And I can just type that all into my calculator the way it appears. 2 times the quantity 1 minus 0.75 raised to the 10th power. And again, you want to make sure you move your cursor out of the exponent before closing the parentheses. And then divide by the quantity 1 minus 0.75. And when you press enter, you get 7.549. All right. You got to be careful about number 2. Again, it's just finding the sum of the first, in this case, 25 terms. So in this case, I'm letting n equal 25. And the sequence this time is a sub n is equal to 2 raised to the n minus 1 power. And again, remember, with the explicit formula, we have a number. We have our first term times our ratio, which is raised to the power. So the base, the thing that's being raised to the power, this 2, that corresponds to our common ratio. So then what is a sub 1 if there's no number there? And remember, we're looking for the coefficient. We're looking for the number in front. So if you don't see it, it means that it's 1. I don't want that to look like a 10. It's 1 times 2. So our first term is just 1. So a sub 1 is 1, and our common ratio, r, is 2. And if I want to find the sum of the first 25 terms, I'm going to go ahead and plug it into the equation. And what I'd like you to do at this point is to press pause and to complete the next 2 examples on your own. Okay, if you've done this correctly, then the sum of the first 25 terms is going to be a sub 1, which we said is 1, times 1 minus my common ratio, which is 2, raised to the n minus 1, which is going to be the 25 minus, I'm sorry, it's not n minus 1, it's just n. Let me fix that. And then I'm going to close my parentheses, and that's going to go over 1 minus 2. And so when I plug this in on my calculator, you don't actually need to multiply by 1 in front, but I will just so it all matches. And again, pull the cursor out of the exponent before closing the parentheses and dividing. And we get a nice big number. So 33,554,431. And the last one, we want to find the sum of the first 8 terms of the sequence f of x is equal to negative 100 times 1/2 raised to the x minus 1. So again, this is in function notation. If I'm trying to find the first 8 terms, that gives me my value of n. My first term is going to be negative 100, and my ratio is 1/2. And so if I want to find the sum of the first 8 terms, I'm going to have negative 100 times the quantity 1 minus my ratio, which is 1/2. Now I do want to be careful because that's a fraction and I want to raise the whole fraction to a power. I'm actually going to need another set of parentheses around the 1/2, or you can simply write it as 0.5 and that'll work also. And I want to raise that to the n power, which is going to be 8. I still have to close my parentheses before I divide, and that's going to be 1 minus 1/2. And again, I want to make sure that I put the 1/2 in parentheses. So this is a lot to type in. I'm going to have negative 100. In parentheses, I'm going to do 1 minus. And then with that 1/2, I do want to put that in parentheses. Otherwise, when I try to raise it to a power, it's going to raise the 1 to a power. I'm sorry, it's going to raise the 2 to a power. So I'll just be dividing 1 divided by 2 to the 8th, and that's not going to give me the same thing. Okay, so I'm going to close my 1/2 before raising it to the 8th power. But then again, I want to pull my cursor out of the exponent before putting another set of parentheses to close my numerator. And then I can divide by 1 minus 1/2. And again, when I type in the 1/2, I want to put it in parentheses. If you change it to a decimal, you don't have to do that. So once I've got it in there, I get negative 199, whoops, 0.21, that's going to round to a 9. And I always round to 3 decimal places. Okay. Here's another problem that deals with an application. In number 4, it says a pool manager wanted to emphasize to lifeguards the importance of treating the swimming pool with chemicals at regular intervals. He performed an experiment by releasing bacteria into a swimming pool and leaving the pool untreated for several hours. The table below shows the growth and the number of certain bacteria in the swimming pool at various times. So if the number of bacteria in the pool represents a sequence, which type of sequence would be an appropriate model? Would it be arithmetic or geometric? And I think, again, if you look at the numbers, it's going from 600 to 900, and then it jumps to 1350, and then all the way to 2000. I think it's obvious that we're not constantly adding the same number to each term. So I think it's probably obvious that we're dealing with a geometric sequence. And so one of the things we're going to have to figure out is the value of r. And just remember, when you're calculating r, you always start with the second term and divide it by the first. And that should be the same ratio as 1350 over 900. And that should be the same ratio as 2025 divided by 1350. And we can check that out in a minute. So if I take 900 and I divide that by 600, I get 1.5. If I want to check to make sure that this works, then I'm just going to start at my 600. I'm going to multiply by 1.5, and I will hopefully see 900. And if I multiply by 1.5 again, I see 1350. And if I multiply by 1.5 again, I see 2025. So I can confirm that this is indeed a geometric sequence and that my common ratio is 1.5. I also know in this problem that I started off with 600 bacteria in the pool, so that gives me an a sub 1 value. So if I want to write the explicit formula, we'll have a sub n is equal to a sub 1, which is 600, times my common ratio of 1.5 raised to the n minus 1 power. In letter C, it says to use your model to determine the number of new bacteria in the 7th hour. So here I'm just trying to find the 7th term in my sequence. And again, I could very easily just keep pressing enter until I get to the 7th term, or I can simply plug the 7 in to my exponent. And so I'd have 600 times 1.5, and I would raise that in parentheses to the 7 minus 1. And we get 6,834.375. And let's go ahead and use units since this is a real problem. And then if we're leaving the pool untreated, we also would probably want to know the total amount of bacteria in the pool after 7 hours, not just the new growth. So in letter C, I'm asking to find the total, and that's the same thing as finding the sum of the first 7 terms. And so if you remember, the formula for that would be to take a sub 1, which is 600, times 1 minus r, which is 1.5, to the n power, or 7. And I would divide that whole thing by 1 minus my r value, or 1.5. And then I can just substitute that all into my calculator. So 600, and then in parentheses, I've got 1 minus 1.5 raised to the 7th power. Make sure you pull your cursor out of the exponent before closing the parentheses, and then you can divide by 1 minus 1.5. And so we get over 19,000 gross. And again, that's bacteria. And then in letter E, it says if the total bacteria count in the pool reaches 35,000, then it's unsafe for the swimming pool. Then it's unsafe for swimming. Approximately how many hours could the pool be left untreated before it would be unsafe for swimming? So you could certainly keep going with your sum until you figure it out, or we could, let's see, it says if the total bacteria, so this is a tough one. I think the best thing to do, because there is a problem like this on your quarterly, I think the best thing to do would be to just keep adding. Trying to think of the best way to do this. Let's use our formula for the sum, right? So we're talking about our sum and our formula, which is going to be 600 times 1 minus 1.5 to the n over 1 minus 1.5. And we're trying to figure out the value of n that'll make this quantity equal to 35,000. So this is actually an equation that you can solve using the graph on your calculator. This is a pretty high-level question. If you go into y equals, let's go ahead and clear out anything that's in there. I'm going to go ahead and put the 35,000 in first. And then in the second one, I'm just going to put that sum equation. So we've got 600. And then in parentheses, it would be 1 minus 1.5. And instead of typing in an exponent of n, I'm going to use my x variable. But again, make sure you pull your cursor out of the exponent before pressing the end of parentheses. And then I'm going to divide that by 1 minus 1.5. And then I'm going to use my graph. You could also go ahead and look at your table. So like if I hit second graph, it'll bring me to my table. And you could just scroll down until you see where the Y2 column ends up being 35,000, and you can sort of see from that that it's happening between 14 and 15. If you wanted to be, well, that doesn't match any of the answers that we have, does it? Did I enter in the right thing? Yep. Huh. If you wanted to be more precise, we could go into our graph. But the one thing you'd have to be careful of with your graph is rescaling your window. So I know if I go to my window, my x-axis corresponds to time, so the number of hours. So I might want to start with 0, and then let's just go, I don't know, let's say 50 hours. And then the y-axis is going to correspond to the total amount of bacteria. So I want my y min, I can make 0. But my y max, I want that to be 35,000. And then if I press graph, I can see that the two graphs intersect. And as long as you can see the point of intersection, your calculator will compute it for you. We probably should have made our y max a little bit bigger. So like if I make it, let's say 40,000, and when I graph it, I should have just a little bit more space there. There you go. So as long as you can see the point of intersection, you can hit second trace, use the intersect option, and then press enter 3 times for the calculator to find the point of intersection. And I must have been looking at the wrong thing. on my table because the intersection occurs at 8.4. And so at 8.4, that's when there's exactly 35,000. So it says how many hours could the pool be left untreated before it would be unsafe. So anything after 8 hours would become unsafe. So in this case, you'd kind of want to round down to the 8 hours because beyond that, it would be unsafe. So I don't know what I was looking at in my table. I'm not even going to worry about it anymore, but I think the graph is the easiest way to do that. The other thing that you could do is just extend your table, but that can be time consuming. I think this is the last problem. So you have two activities today. One is to practice doing sums of sequences. So you're going to be doing a sum of geometric sequences, but it'll also give you some practice on coming up with the explicit equations that correspond to these sequences. And then there's also a gallery walk. If you notice around the room, those equations or those graphs that we did a couple class periods ago are still hanging. So the second half of the class, what I'd like you to do is try to come up with an equation for each of those graphs. And so you'll need your foldable to help you to do that. It's really important that you guys can recognize the shape or recognize the parent function from a graph and then understand the transformations and come up with an equation. That's a really, really helpful skill to have. If you don't finish the gallery walk during the period, that's fine. Just submit whatever you get finished. I just wanted to make sure that you guys had enough to do. There is an exit ticket as well on the back of your warm-up, so just make sure that when you are finished with the practice of the sums and sequences that you do the exit ticket as well. So let me squeeze in the exit ticket. So the first thing I want you to do is that practice. Then I want you to do the exit ticket. Turn both of those things in. And then if you still have time, do the gallery walk. And if you don't, like if it takes you the whole period to do that activity, then that's fine. But if you are able to finish that early, I'd like you to do the gallery walk and get a little bit of practice. And I might be able to give you a couple extra points for that if you're able to finish or get about halfway through. So anyway, again, I apologize that I wasn't here today. I will see you next week. Have a great weekend.